do we want? No, can I switch on the? The
presentation.
Presentation.
Yes. So if you go to the right.
What?
If you go to the right-hand side, there's a thing. You open open the collaborate panel on the. There's a purple button.
Wait a minute. Oh, right there. Okay. Yes. How's that?
And then if you go to, someone just asked whether you're in a spacecraft, but that's, I'm not sure.
No, it's my office. It's actually an office.
If you go to share application and screen.
Where the hell is that now? Share application and screen. Open session.
Oh, if you go to.
I can see the share content. Share.
Yes, and then go down to that menu. It's the second one on the share content list.
Wait a minute. You can see me down there. Now, where the hell's share content list? Presenter. Video. Oh, here. This one. Okay. Yeah. That's share. The share video. Is that the one?
So then you go to share entire screen. Has you got a drop down menu? Have you got a little thing there that
share entire screen? Where the hell is that? Jesus. Share. Close the panel.
So if you go to the panel at the bottom, and then there's a little there's a button
on the bottom. Which side? Left or right?
Oh, right hand side. It says open collaborate panel. Is there a purple button there?
I'm hitting. That's it. How about that? We're getting there slowly. Can you see anything better now? I mean,
not yet.
It's expanded the. I've got.
No, we can still see you, Mick. We can't see your presentation yet.
Well, I've got it here. What happens if I?
Could you send it to me?
Yeah, I did. Now wait a bit. I can open it here. I mean, let me just open it on here. Hang on. Try it. Here we go. It was all ready to go. Of course, everything was. Let me try this one. Quebec. Here we are. Now that is the.
Yeah, we can't. We can only see you still, Mick. We can't see you. We can't see the.
Can you see the presentation, which is on my screen?
No, we can't.
Okay. Now let's see how the hell I can do this. How do I get?
Have you found a thing called the collaborate panel? Open collaborate panel.
Open collaborate panel. Where in the screen is it? On the left or the right?
That's bottom right hand side.
Oh, open collaborate panel. Yes. Okay. Right.
And then if you go to share application screen, can you see that?
Share application screen. Share content. I've got share content.
Yeah, what is that? Is that yes? Share content. Yes.
Oh,
good. Click on.
No. Oh, yeah, I've got it. Yes, we're getting there. That's it. Share. Now, that's opened up a new little.
Yes, and then when you do that, you say share entire screen.
Right.
In the drop-down menu, there's some choices in the middle.
In the middle. Share. Stop sharing.
Yes, there you go. Yes, that's it, Mick. And so now now what you have to do is to click on your presentation.
How's that?
It'd be behind
My
it somewhere. Yeah. Your presentation, as if you were. So it'd be behind that the screen,
It'll be
behind this
here
window.
somewhere. Good God. Share application. Right.
No, you're the right thing. You just got to get behind this panel, which is you got to get behind this.
What I've got
you gotta
is I've got a panel disappearing into infinity. With
Yes, yeah, we can see that. But all you need to do is you need to click on the presentation, which is behind that window.
Well, what about stop sharing? No.
No. This is all of this is good so far. You just need to get behind the open. You just need to open the window that your presentation's in. If it's a PowerPoint, you just click on the wherever that PowerPoint is behind.
Oh, wait a minute. It's here. Must be here. Okay. Ted. Okay. Blocks. Wait a minute. Could I go into my? Oh,
Yeah.
here we. I see what you're doing. Right.
You had it for a second.
Yeah, I
Yes,
know. I'm trying to get to. Oh, Jesus. The trouble is that it vanishes all the time. Shit, this is difficult. Wait a minute. KM6 blocks TEDx. We don't want that. We don't want blocks. What I want is here we are. Documents. Documents. Here we are. I'll get to it now. I managed to get this on the. I've opened up my documents. Here we are. Q. Sorry, this is maddening for everybody. I'm getting there. Huh? Public lectures. Here we are. Well, that's no. It's on my screen.
Yes, it's on our screen too. So if you just go to the presentation, like full screen, yeah, that little, yeah, perfect.
How's that? Is it?
Well, it's okay. Yeah, but it said that we can't see the movie, but maybe you need to press that to.
Don't worry about the movie. That's just a joke. I think we've seen enough movies. Can you see Africa with Zimbabwe on it?
Yeah, we're in business. Thank you.
Okay, sorry about this. Look, now that you've seen Eastgate, you can see what I'm trying to do, and why I'm very worried that architects don't seem to understand that it is part of architecture, that the green movement ends up changing the architecture quite radically. I mean, I did Eastgate it was finished in 1996. It's a long time ago. Since then, you know, things have completely changed. PV is now very much cheaper. And at the moment, we're running here on solar completely at night, thanks to the batteries, which don't work very well. Zimbabwe is going to the map in front of us. You can see the two bands crossing Africa. Can you see that? Hello?
Yes, we can see that.
Okay. Those are the crisis zones, and poor old Zimbabwe is right in the middle of a crisis in the southern half. And you can see the changes. We've done the old map and the new map, and you can see how the geography is changing quite radically. We seem to be getting a lot more rain on the east, and it's drying out radically on the west and in the south. Now, the crisis zones are causing huge movements of people, and you can see the arrows on Africa moving up towards Europe. In the southern half, they're all over the place. They're moving away from the dry, from the heat, from the drought, and moving towards where water is and where there's food and work. Now we'll go to the next slide. Zimbabwe is a mid-altitude climate, like Mexico. It's 15 south, and altitude's 1,400. I said that earlier, which means you get very clear skies, and that's why you get a seasonal shift. That you get about 9 months of this picture, and about 3 months of that, which is rain and greenery, and higher humidity. Because it's up at 15,000 feet, you get a diurnal shift. 1,500 meters. You get a diurnal shift of about 10 degrees. And that actually causes a change to the architecture. Now, this building was built in 1100 AD, and it's Great Zimbabwe. And it has, it's this beautiful stone wall. And I was wondering how it's 3 stories high, and it's about 16 feet thick. That's about 3 meters thick. How on earth did they build it without scaffolding? I said to the guy taking me around it. And he said, well, that's easy. They just had a stepped end. So you walk up at one end of the wall, and you just build it as you go up. And that enables you to build a curved wall. Very exciting. And then you look at the stones, and you can see how the coursing follows beautifully. So they don't have each stone in a course. It's about the same height. That indicates that the stones were cracked by the diurnal shift, the day and night temperature on the surface of the rock. And they made the blocks by cutting them somehow. We're not sure how, but it could have been wedges of wood in cracks, which they then throw water on, and the wood expands and cracks the rock. Or it could have been fire, it could have been many things. But they took the blocks off the quarry rock and placed them on the wall in the same order. And that's how they got this marvelous flow of coursing. So in a way, it's an expression of the diurnal shift. It's an expression of nature. And then nature ends up by painting it with lichen. Isn't it a fantastic story?
Yes,
I'm trying to show you why I believe that green changes architecture. This was my first house after I came back from the AA, and I built it all in local stuff, local timber and local timber gun poles and so on. And then I actually, from the AA, I came full of classical architecture. I was keen on modern, but I thought it lacked so much, and I was looking at Rome here and wondering why, if you have a city that's all walking, and the Romans built cities with 3 building forms: the colonnade, which was peristyle, the forum, which is the piazza, and then the temple, which is the object building. So I tried to. That was one of my. This was way back in 1986, where we built a university building, just open colonnades, really. And the colonnades connected other buildings together. So the buildings, the peristyle building is a linking building. And I thought that was such a brilliant idea. But the climate works very well for that. You can move around under you're mostly worried about the heat of the sun, actually, in this climate. And then I started in town. I built this office block on the left with the green shutters. And none of the other buildings had sun shielding. and I wondered why. It made a huge difference to the heating and the cooling systems. And we made these locally, actually. This is extruded aluminium. And then we formed these courtyards which gather night air like a reservoir. And we put plants in them, and you actually reduce the temperature. Now, at this stage, I was building with full air conditioning. And the air conditioning plants have never never had to be used fully because of this shielding on the outside and plants in the courtyards, and the courtyards used for collecting night cooled air and so on. This was sort of background leading up to Eastgate. The first block I built in Harare was naturally ventilated and naturally cross-ventilated. And I found it was a big problem because people would never open the windows at the right time of day. And they tended to keep them always shut. And so you never got it. It never really worked properly. It looked quite nice, but that was all. We had these floating gardens to enhance the updrafts on the outside. And then we got Eastgate. Now I don't have to tell you about Eastgate. We can answer questions about it, but I'll skip through that. And here I've been through all this. It might be interesting for you to know how I think the termites build these towers. And I think the thing is, the terrain evaporates, and if each blind termite builder places a lump of clay injected with his own pheromone in a position where the smell of the previous laid brick is strongest, that's actually where the wind is not the strongest and the sun is not the strongest. It's in this sort of lee of the wind, and that somehow forms this shape. So in a curious sort of way, the architect for this building is actually the sun or the wind. Now that, in a way, it describes what's fascinating about these towers is that they are built to optimize the exploitation of natural forces. So in a way, it's the perfect model for Eastgate. We could never do what the termites do because they spend their whole time forming and building. The moment this falls down, they build another one. Anyway, I thought that would be interesting. So we don't have to show you any of this now because it's all been explained in my rather. I do sound a bit like Joe Biden with my mumbling, but I hope you understood most of it. Okay.
Yes, yeah, we did.
Okay, we're going right through it. The interesting, we were able to use local labour who were excellent at building in stone and in concrete. They took to precast concrete so well, and we mixed various gravels and stone and sand to get the color we wanted, and then we made formwork which collapses. You can take it apart before the concrete sets, so you can sort of peel off the steel forms and then brush the surfaces with a wet brush to get this stone-like effect. So they looked as though they were actually made of stone, and that's how we get this effect. It was beautifully built, actually. They were very, very good builders. Somehow because they built Great Zimbabwe, it's in their blood. They're very good at it. Anyway, there's loads of stuff here, which this building was designed and built with very close collaboration with Arab. In fact, Arabs came in. The first meeting we had on the first day before I thought of anything was a meeting with the engineer, and I think that's terribly important. You'll never get to this degree of I suppose, science and maths behind the design unless you work very closely with the engineer. Now, then I got a call from a friend who'd moved to Melbourne, and the next series shows how we apply the same principles to a different climate, completely different climate, to a different culture and a different economy. It's really the third world technology exported to the first world. Now, Australia has this curious, in the south of Australia, has this curious weather created by anticyclones that flow across the continent. And there's Melbourne right south. It's about 37 south, and it's on the sea. And that's a picture of the weather, and it's a very good picture. If this is the sort of picture architects need. All you get from engineers is averages and stuff and figures, but you need a picture of it. And the red dots show the diurnal swing, the day-night swing. The red is the maximum day temperature. The blue is the maximum night temperature, and it swings in the curious 3-day cycle, which is to do with those anticyclones moving across. As the wind changes direction, you get heat off the desert, which is very hot. And then the next moment in the cycle, you get wind off the Southern Ocean, which is cold. It's a huge difference. I mean, it sometimes goes from 46 down to 18 in about half an hour. Curious, and in the middle of it all is the yellow band, which is comfort level. Now, if you understand that, then you start designing. And the next thing, of course, is its position in the city. Now, the building I'm talking about has these 6 turbines, the yellow turbines. So it sits inside a 40-meter high city with narrow streets, only 6 meters wide, so they're 40 meters high. So there's a lot of shadow, and there's a lot of fall off in light. That's the plan of the building. They wanted an open plan, and therefore, when we wanted to create a ceiling which would absorb heat from people and absorb heat from machines, and also and we would probably cool that down by opening windows at night. And then underneath the ceiling, we would have chilled panels, which are with cold water. So the wavy concrete ceiling is what we call a passive cooling system, and the little dishes underneath the ceiling are chilled panels, and that's active. So remember that. And then you can see this, the north is directly up and south is at the bottom. West is on the left and east is on the right. Now, the cooling system we used was what's called displacement ventilation, which is like the guy sitting at the bottom left. He's very happy because the air is fed in around about his feet, but it's fed in with swirl diffusers, which don't make his feet cold, and he can adjust them. And the hot air then rises up and is exhausted at the top. Now, the normal air conditioning system drops cold air from the ceiling down on top of the man, and it is recirculated 6 times an hour, whereas the one on the bottom left does not recirculate any air. And the same applied in Eastgate. I do not recirculate air. And I'm very pop now because with COVID-19, people are getting more and more worried about the the air being recirculated. They like the fresh air. The fresh air is certainly better from the safety point of view. You can see that the diagrams show that humans give off 80% of their energy in the form of waste heat. And the machines, well, the old computers are about the same as that. So you can see these sort of columns of heat rising up into the top half of the room. So all of this, it's engineering and architecture, and the form comes from that study, and that's what it looks like. I don't think no one's ever going to build a wavy ceiling again. It was great fun, but there were a lot of technical problems for partitions. So it was really meant for open plan. You can see the plants are very good to have in an office. They kind of work very well with humans, and with the air conditioning system I've described and the fairly low light levels, they actually don't need replacing. They did very well, the plants. Normally a plant in an office has to be taken away every 3 months and replaced. This didn't happen in our office. That was the sort of canary in the coal mine test for good air conditioning. The air conditioning system I've described was extremely popular. That was the most successful thing about this building was the displacement ventilation. People who suffer from dry air and recirculated air were very happy with the displacement system. So we're not using air for cooling. Air is used for breathing. What we are cooling by radiance. The ceiling absorbs people's heat, and that's aided by the concrete ceiling does about between 10 and 20% of the heat load, and the chilled panels do the rest. Chilled panels just have cold water, about 15 degrees, circulating through them. And then the windows, we spent a lot of time on the windows. The windows were timber frame, because aluminium frame is a bridge, cold bridge, and as you know, or a hot bridge. So timber is much better. We have at the transom running across the door height on the window are chilled beams which drop cold air in front of the glass, and then the glass itself is we have used a reflector. It's low E glass, double glazed in Melbourne. Most of the light comes from reflected light. This we're looking at is on the south side of the building. That's the opposite to the equator in Melbourne. And strangely, the glare was much greater from the south because of reflected light. And the plants that we grew in front of the glass helps to break up glare. Okay, so there's a lot of physiology in this. We're thinking of human physiology. The window has grills at the bottom letting in warm air for the winter, and always in front of the glass. And then the ceiling is cooled at night by automatic windows that open and just let the outside air in. And because of the diurnal swing, we're able to use that day and night temperature to to cool down the concrete. I'll show you some more maths on that. That's how we built it in huge concrete sand. Now, in Zimbabwe, we couldn't do this. You know, this is that weighs 10 tons, that unit. So the whole technology is very different, and you can count the number of people on the site. In Zimbabwe, we'd have about 2,000 people. Here we only had about 6, or no, about 10 perhaps. So the whole technology and building method is quite different. On the outside, the windows at the top of the building are smaller than the ones at the bottom, because that worked well with the light levels that drop off as you go down into the streets. And it's quite significant if you take a light meter and you simulate it. So the windows at the bottom are bigger, wider in area than the ones at the top to let more light in. And that corresponded very well with the ducts that run between the windows. That have to be bigger at the top and smaller at the bottom, because they're exhausting. The ones we're looking at exhaust the air, with the turbines at the top just peeping over the top. And then the slot formed in the duct with the windows set in are the ones that open automatically to let night air in to cool the building. And then we have balconies that people can walk out onto, and they are now completely covered in plants. That's just you'll probably see later. Now that you can see the termites. I keep on going back to termites. The termites in Darwin are really amazing. Look at that huge cathedral, they call them, on the right, and how the same principle, the surface area controls, enables them to modify the internal temperature. And this just shows the opening of the window to let the night air in, and I think that is the proof that it works. The blue line, light blue, is the diurnal shift, which more or less follows the pattern I showed you earlier. The red line, or the brown line, sorry, is the temperature of the concrete ceiling, and the blue, the dark blue, is the resultant internal temperature in the air. So you can see, and actually, it's a bit. Sorry, it's not quite the air temperature. It's a formula, an algorithm which we developed to combine the radiant effect on comfort as well as the air temperature and that gives you the dark blue line. Rather complicated. So remember, our skin is more sensitive to radiant heat and cold than to air temperature, heat, cold. So it's quite significantly more. So it's actually a good idea to cool people by radiance, because cooling is by far the biggest consumer of energy. The red zigzag at the bottom is the opening and closing of the windows, and you can see that when there's a peak in temperature, day temperature in the light blue line, you don't open the windows because you don't get enough. The air is too hot to cool the internal building, so the windows don't open. All of that is controlled by an incredibly complex system. Computer control system. I think we had 2,500 probes in the concrete, measuring the temperature of the concrete, feeding that information, that data into the controlling system. So that is how it works. Sorry, is this being heard and understood for everybody, or am I just rattling on? Is
no,
it okay?
Yeah, it's brilliant. Yeah, it's really interesting. Yeah.
Sorry, it as you see, it's a combination of engineering and architecture, very close.
But are you working alongside the engineers as you're designing it,
Yeah.
or?
Yes, there's a picture of us all. There were 14, 20, nearly 20 people in a room, and we designed this building as a combined team. Engineers, architects, facilities managing people, QSs, mechanical engineers, all the engineering was there. And even the client came in occasionally. But we met every day without fail for 2 weeks. And we worked 6 hours in the room. And then we went home to our offices and drew what we'd agreed in our own interpretation, and then came back the next day and did the same thing for 2 weeks. And we were paid to do this by the client, by the hour. And we ended up with this building, actually, more or less. So it does pay to have a very concentrated sort of, a concentrated workshop every day. And you then end up with the same picture in your head. Sorry, just tell me on something.
Yeah, no, I was just going to say, how did you persuade the client that this was a good idea? Because I mean, before the building's finished.
Well, luckily the client was an architect, you see, and he was a friend of mine, and it was his idea, and I said, it's going to be difficult. In fact, the structural engineer, was a brilliant guy, Italian guy. And he said, this is crap. I'm not going to sit here every day for 2 weeks. I've got an office to run. What the hell do you mean? And at the end of it, so halfway through, he did most of the talking. And at the end of it, he said, this is the best thing I've ever done. Because everybody knew what everyone else was thinking at this stage. And the job just went through documentation very, very quickly. We were on the same page all the time.
Yeah.
So it's well worth trying. It was hell for me, because I had to sort of, I had to give away all the time, which was difficult and tiring. But I think it ended up well, actually. Anyway, you can see each elevation is different because it has different conditions. So all the time it's about relating and interfacing with the macroclimate of the site. And that's what makes each building completely unique. This building looks totally different from Eastgate. And luckily, I had a brilliant draftsman who made these wonderful drawings of how it works. So it has wonderful, you can have all this if you want to go into it in great detail. How the balconies work, how we decided, in an office block, everyone says, well, they always want a window. Everyone wants a window, and you can't have it in a big office block. So we decided to make the passageway next to the windows public, and the desks were pulled away, and it meant that it was a breakout space, or place where you could meet. You could go and have a telephone conversation on the balcony, particularly if you didn't want other people to hear it. And also the balconies when we finished is absolutely amazing. We started off trying to get plants to grow, and I tell you, in Australia, when that north wind blows off the desert, it burns up just about every plant that's ever existed. These were very tough, hardy plants, but they never really made it. And we ended up using geraniums. Geraniums are amazing plants. I love them. They've got furry leaves. They come from the Eastern Cape. They don't come from Australia. And just look at them. They love being burnt by the wind. They don't mind it. And it's the fur on their leaves, and it's very similar to the cacti. You know, it's all about surface area and heat dispersal. And it's funny that architects looked at this building and said, it's not a bloody office block. It's what is it? Housing? What is it? So they didn't like it. The local architect didn't like it at all. The facade on the west is all made of recycled ancient timber. The eucalypt in Australia produces hardwood, very hardwood, and it lasts forever. So this timber was untreated, and it was cut from ancient wool warehouses. I managed to find these huge chunks of timber, and we got a guy cutting them into small planks, and then we attached them to. You'll see it on another slide. But you can see how, you know, plots on a building need a kind of architectural framework of sorts, and they've got to be looked after. But fortunately, we had somebody to do that who really enjoyed it. So there it is. It's got, you can see the 6-meter wide streets and how the light falls off. Now then we did simulations. The difference between this and when we were designing Eastgate, there was no software at all. And Arabs in London did all the building physics for me. And I never really saw it, but in this, when we got to, this is 2002, that was designed, we were able to simulate the light levels before we built it at each level. And that gave us the idea of making the windows smaller at the top and bigger at the bottom to balance the floor-to-floor penetration of light, natural light. And it's rather like, it's like referring back to nature. If you look at a forest, sorry, I'm not talking about a conventional forest, I mean a commercial forest, I'm talking about a rainforest. You'll find that the trees are all different heights and they're different ages. And that enables the light to come in at all sorts of different angles. And that's how they survive. So in a way, a city could be more like a rainforest, actually, for light, if you're talking about getting light down to the streets. This city was 40 meters finish. Everything had to be 40 meters by law. But it didn't really work for light. But anyway, we ended up making the windows smaller at the bottom, bigger at the bottom, and you can see the tapered exhaust ducts running up between the windows. So there's the facade. Now the ducts on the north side are dark color, and that's another thing. Albedo, which is the reflectivity of color, is very important if you're worrying about having energy. So black ducts help, or dark ducts help to pull the air up. The turbines on the top were much more cosmetic than I liked. It's one of them works beautifully, but the others don't work. They don't work well in cities because the winds are so difficult in a city with all sorts of different directions. We chose the Savenius vertical axis turbine because it doesn't mind. It's meant not to mind the direction of the wind, but we made them too heavy. Something we now regret. It was a nice idea, but it's I wouldn't do it again. Actually, it's not worth the while. They look nice. So there you have the two: the north facade, the south facade. South facade is silver reflective because that's where the air is down from it's treated on the on the roof and pumped down and fed under the floors on the south side. The pipes in between on the windows are made of ETFE, so they're transparent, and they are cooling towers. They are shower towers. They just have, I don't know if I've got a picture of them. Yes, there they are. They have a shower head at the top, and they circulate water and which drops like rain, and that provides cooling for the shops at the bottom, and it humidifies the air. So it's quite nice air actually, because if you know the smell you get after rain, that's how it smells. It's very nice. There's all sorts of problems there in Australia with Legionnaire's disease. Talk about COVID-19. Legionnaire's is a horrible disease. It's a real killer, and you get that if you're not in all water, particularly in droplets. So we're now picking up aerosols. So you want to avoid aerosols and get the right temperature to avoid Legionnaires. Oh, there they are. Yes, that's the way it's just dropping water through a contained cylinder. We had a terrible job cleaning them. I think there's a picture of a guy being lowered down inside to clean it. So we tried the whole idea of this building was to try out everything. So it was council offices, and it did have a huge effect in Australia, because while we were building this building, they brought in the star rating system, the building, the boxes, ticking boxes system, which was partly copied from BREEAM, which was worked out in UK much earlier. But the effect of building this building by council and trying out everything had an enormous effect on the whole development of new office buildings in Melbourne and in Australia. We had great fun with this. These are hydraulically operated fins that, and the hydraulic system is controlled by a computer. So, and you can do all sorts of patterns with it. So it makes a very lively, dynamic facade. In fact, I think this one was the Mexican wave. You have to do it because occasionally they crash into each other. So it took a lot of error, but we got it to work in the end. But I was quite keen on this idea of dynamic facades that actually move with the weather. The same way a tree or a thing in nature changes, like the sunflower opens and shuts with the sun. So the western facade opens for most of the day and just shuts as the sun comes round in the west. And so you get a view out for most of the day. It's just in the afternoon you don't get it. Don't get the view. And the eastern facade was a permeable facade to naturally ventilate the dunnies. The dunny is an Australian word for toilet. And we reckoned that they needn't be ventilated or air conditioned. So they were naturally ventilated like that. It seems to work all right. No one complained. And then the roof, the client wanted the same area as the footprint of the building in plants. So we more or less achieved that with the rooftop and the northern facade, which has plants. Otherwise, it's full of plants. And we tried to get people to use the roof, but you need a bar or something to get people up there. They won't use it much. There's the turbines. We had quite fun with the turbines because they insisted on us using the turbines to generate electricity as well as pull the air out. Well, I met a guy who was making turbine generators with second-hand motors from washing machines made in New Zealand, which have a very large diameter, and you can convert the electric engine, to a generator quite easily with a bit of wiring, and that makes a very efficient generator for a turbine, because you don't have to gear it so much. So there were a lot of things like that were going on while we did this, and we had a very good client. So there's the building. You can see that the energy is moved around this building, not in air with air in ducts. It's moved around with water, and the water picks up the heat from the offices, takes it down to the basement, where we have phase change material that absorbs, that's a huge thermal capacity, which I'll explain a bit later. And we use that as a heat store. So whereas in Eastgate, I was able to use the concrete structure as the heat store, the thermal store. This one, we had to invent separate heat store. The red line, the brown line is the exhaust, the blue, light blue is the air feeding in. And I think the next, yes, there we are. In the basement are these huge tanks, sintered tanks, and in them are stainless steel balls with phase change material, which freezes at about 15 degrees. And we freeze it by circulating cold air through these tanks. And that cold air is cooled when the diurnal shift allows it. In other words, at night, or when there's a cold wind off the Southern Ocean. This is all picked up by the computer. So what we're doing is storing the cooth, the cold energy, in phase change. Phase change is a mixture of salts, highly corrosive salts that are placed in a stainless steel jacket. It's about the size of a cricket ball. And you can see the freezing curve, which allows it to store energy, enormous energy, as it changes state. So phase change means phasing a simple change of state liquid to solid. It's how a refrigerant works, but this is a very simple form, and you can get your. Actually, I used a guy who has an engineering works near Cambridge, and he did all the development work for this, and it needed, the trouble is that we were trying to do so many things that we rushed through with this system of balls, which work all right, but if we'd spent a lot more time and energy on developing a better heat exchange, we would have made it work much better. So this is an area that it really is worth pursuing. Phase change materials are very, very good. It's a very good idea, and this guy in Cambridge is an expert at it. That's how we made them. We had to make the balls in China, of course. He never told us what salts he mixed together, because that was his patent. And then we drilled a hole in the basement into the main sewer in the street opposite, not the building sewer, but the main city sewer. Pulled water out of it with all the shit and crap, and filtered it, and then pumped back the solids into the system. And the idea was to find water. Water is a very scarce commodity in Australia. And we worked on this for about the guy that contracted to make the plant worked on it for 3 years and actually failed to get it to work. And eventually we had to bring in someone else to do it. But I think they've got it to work now. You can take a huge amount of water out of a sewer, and it doesn't affect the flow rate of the sewer. And it's certainly worth doing. You can also withdraw heat and all sorts of things from a sewer, which is cheap. It's energy going wasted. So you can use it for heating and for water, straight water. And that was just to show that the animals liked it. So that's I built a hotel for pigeons. So I created quite a stir in Melbourne, and they let me do all sorts of crazy things. This was a building. Sorry, does this interest people, or have you had enough? I can go on for an ages.
No, it's great. Really good. No, it's great.
Is it all right? Okay. Well, this is quite fun. This is a huge plant that's built in the south of Australia, in Gippsland. And it's downstream of a huge paper mill. Now, if you've ever been to the bottom end of a paper mill, it's absolutely disgusting water. It's black, it stinks, and it goes into the river system. And this plant was built to recycle that water. And you can see the water that this building sits on is beautiful reverse osmosis, clean water. Now, the purpose of this building was meant to be to sell the idea of water filtration, recycling water, and how important it was. And particularly if this is about the worst you can ever get. Heavy metals, all sorts of terrible things come out of a paper mill. The idea was to make this building show the physical properties of water. And so I built this thing. It's made of, it has, look, I don't like this building because I think it's a bad idea. But the client and everybody wanted me to do a symbolic form and make a building out of it. Well, for the purpose that we wanted, which was a visitor centre, symbolic forms might work. So it looks like a sort of shell thing, and it's made of aluminium. It's quite an interesting technology because these are actually, this is when I learnt AutoCAD for the first time, because I had to make the building, I had to draw it in CAD so that it could be made. And these are, they're all geometrical shapes, but the curve is a cylinder. It's a donut. Each is a donut, and you get a tapered strip, which is worked out by the computer, and then it is formed actually in Singapore, and then shipped over as flats, and then on site. Now, the idea of it was that there's a pipe on the top of the building that circulates water to run over the surface of the aluminium and into the lake. And the idea is that at night, with these clear skies in this part of Australia, you get huge amount of back radiation. So that water cools just by back radiation. You don't do it during the day because you get too much evaporation. And the water is very expensive, so you don't want to lose it. So it's done at night, and it's cooled at night. And that cold water falls into the lake, sinks to the bottom of the lake, and then we are able to pump it up to cool the building inside. So it's just using the water as the thermal store, and the building can then be very light. You don't have to worry about thermal mass. That was just a I'll just chuck that in. And then I got to China, at Dongguan, and near Hong Kong. It's actually near Shenzhen on the mainland. And this one, I think, is yes, I built various things. One is a tower we built to try out what it's like living in a tower. And in China, all the buildings, the housing buildings, are 37 stories. And if you go up vertically, your plumbing and your wind and your windows, all sorts of things begin to change because of air velocity, and all sorts of build up of gravity is the biggest problem with water, wind pipes and things. So that was the tower, and then two is the thing I'm going to talk about, which is a dining hall made of containers. Now China actually has to get rid of 1 million containers a year. Once the container has done its 10 years of service, it cannot be used because it loses its validity, its structural validity. It starts leaking and things. So you get these amazing things. Now, in China, I said, look, we can build with these, but I want to see what they look like. So they said, all right, we'll put them up for you. I tell you, in China, they do anything. They just do anything, and they don't hesitate. They're fantastic people. So I said, well, we'll build this building like Stonehenge with just vaults with arches, and they'll be separated in the arches with 300 mil gap, which we'll fill with concrete, because actually, although the container is very strong, there are all sorts of fire problems with steel, as you know, and so the structure actually had to be concrete. So the containers are really formwork for the structure. So there's the plan. You can see the black line is concrete, and you get these quite interesting forms. It's a restaurant with little bays get out, and then a kitchen at one end, and so on. And the thing about it was that we were in the middle of a huge development, which was very green. And I tell you, the Chinese are going to get there first when it comes to green architecture, green development. They had covered all their buildings with PV, and so there was no need for solar power, but there was a huge need for solar cooling. So what we did was we used the vac tube hot water harvesters, which we put on the roof in an array. That water was then at about 87 centigrade, was pumped into, it's not on the drawing, but it's an evaporative chiller. The evaporative chiller, absorption chiller. Got the wrong name. Absorption chiller is like a reverse. It's like a refrigerator actually, but it works with hot water, and it can produce cold water at about 12 degrees centigrade, which is then pumped into the tank at the bottom of the building in the basement, insulated tank, as a thermal store. And then we can pump that cold water to cool down the beams that are formed between these black lines between the containers, with pipes, cooling pipes, and we can also make cooling slab. And then the big highlight of it was this was designed by a German engineer who's a very good friend of mine. He makes these waterfalls in cold water, Now, there are the beams with the pipes in them being laid, and the concrete, before the concrete's poured, and the cold water will be circulating to cool down the beam, and the beam then is a radiant cooler. There's the building sitting in the middle of this development with a marvelous lake, which contained, what they did was all the wastewater went into the lake. And then they had 4 little goldfish swimming in the lake as the test for the purity of the water. But most of it was purified like a wetland. It was sort of constructed wetland in the middle of the whole development. Anyway, there's my building with the array on the roof, and even a garden on the roof. And there is in the middle, at the end of the dining hall, is water in a curtain. Now that is, I think there's a better picture. The water must flow down a stainless steel fabric. It mustn't splash. It must remain locked into with its surface tension, and it's at 12 degrees. And the air temperature in this building is about 25, but very high humidity. So that condenses on the curtain. So it's a dehumidifier as well as a cooler. And we place this between the servery and the main hall to stop the smells and stuff. And there we are. It's just recirculating. You see, the important thing is not to, if it splashes and you get spray and aerosols and things, you get all sorts of other problems. But it worked very well, and it looked marvelous, actually. Really, it felt cool. I think this is meant to be a video, but I don't think we can we show it? Chinese love showing off. Give me a chance to have a drink of water. There we are. Right now, how do we go on? There we are. Yes, then I mean I can go on. This one wasn't built actually, but it's quite interesting. if you like. If you're not bored and fed up, how are you doing? I, it's
No, we're good.
Will.
We're good. Yeah, we're
Yeah,
absolutely good. Yeah, one more project would be great.
would it? All right. Okay.
Yeah.
Well, look, this one. Shows how completely crazy the Chinese are. They'll do anything, you see. And they said, we want you to build a greenhouse in Dongguan with a tropical greenhouse with huge trees, and we'll go to Yan'an and we'll choose a tree and we'll bring it across and plant it in your greenhouse. Now, they're very good at planting trees. They're astonishing, and they do the landscape before the buildings always. They're very good gardeners. And the size of the tree is absolutely astonishing, how they can somehow move a tree from one place to another, and it lives. They sort of bandage it up, put it on a truck and carry it, and then they plant it. And I'm talking about huge trees. I mean, sort of a meter diameter. It's nothing. Anyway, so I went to Yunnan and we looked at these amazing trees in the rainforest and had an incredible time. And then when we were there, I saw this. This is the Mekong. And you can see the mist rising. Now, the mist is actually made by the trees, and it's how rainforest works. About 25 to, I don't know, 50% of the rain in a rainforest is made by the trees themselves. And there's all sorts of science there, which is fascinating. It's well worth getting into. And the trees, as I've explained before, have this they're in layers, so they have of light, all sorts of fascinating things. But the life in a forest like this is up in the canopy. There's very little going on at ground level, and then there's a huge amount going on underneath the trees. I don't know if you've read the marvelous German book about called Tree, and how the mycorrhiza, which is a fungus, links the trees together. In fact, they have to be almost told what to do by the fungi that controls the forest, and they trade sugar or hydrocarbons for they give back nitrogen in exchange. So there's a trading system going on there. And plants, of course, came after fungi. So plants and fungi symbiotically rely on each other. And I've seen fungi kill trees whenever they feel like it. So there's as much going on under the ground, under the forest, as there is on top. When asked to build a building like this, to think of planting a tree and then sort of it grows, and the building has to change with the tree. So it's a tree in itself as it grows up, and you have to have access as it grows up, and then you have to prune it, otherwise it'll go through the roof. So I was very on ETFE, which was used in Cornwall. And so we got very excited about that as a cocoon, because actually the climate in Dongguan, where we were going to build this, is not like the Mekong. Although it's in the same latitude, you get a cold monsoon from the north, and that would kill most forest trees. So you have to balance that. So they needed a building which would change with the weather. And you also had to dig. Sorry, these are my curious drawings. I had, at this stage, learned how to draw in AutoCAD, and I went completely down. I don't know if you can understand any of this, but the problem was that we had to make we had to excavate down into the earth and change the structure of the soil under the tree to get it to work properly. I mean, a tree is, top left is a diagram I drew of what a tree is. A tree is a bridge between, if you like, the water table and the sky. And in between are the animals that are very important. And there's the decaying system of the tree. The tree drops its leaves, and that's how the minerals get recirculated. So it's all about, systems, physiology. So we're talking about the physiology of the tree to understand that, and so on. Anyway, this building, I wish to God we'd built it, because it's a 40-meter diameter, 40 meters high, and it had a roof that had to alter with the weather to let in. Because the problem is that in the middle of the day you get too much heat, so you have to put a hat on it, and then that's got to open up, so you get fresh air. So you really are encapsulating a tree to make the internal environment as near to a rainforest environment as possible. In that way you learn, and the whole idea of this building was to teach people in landscape architects in cities how to fabricate the greenhouse to make it work for the plant. Yes, it was quite a job. I spent hours on it. Anyway, now I think this is the last lot about it. It's back at home, and it's curious that in the 20 years I was away in Australia and China, came back home, and the city of Harare has moved from the garden city with a cluster of offices in the middle to a hub. It's no more than a hub. It's a place you go to go somewhere else. And there's Eastgate, and surrounding it are street vendors. And the site next door to Eastgate was going. The same client wanted me to do something there, and he wanted me to do a car park, and I said no one can afford a car anymore downtown. What you want is a street market for vendors. So that was the site, and we had to. It's a long story of how we managed to do the demolition, because the streets were actually full of vendors. So we built this building. Now it's actually finished now. These were just sort of sketches of how it would look. So it's a very simple building with just open structure. And then we built these stalls. Now, what's interesting is that the whole city has changed so much, and the market has changed, and the people, the offices. This was for 20 years a full office block. The offices started leaving, and because of the chaos surrounding it. So I've now been asked to change it into housing. And because I had put the air ducts and the services down the middle, all the wet services, we are able, we haven't done it yet, we are able to convert it into housing. So in a way, this to finally finish the talk, I think for the future, the building has to be, it has to respond to the climate, to the culture, and to the economy, but it also has to be adaptable, and adaptable without much cost to follow the market. This is how people live at the moment in Harare. And they live under anything they can pick up, and it gets knocked down. So we this goes into low cost housing, which I don't want to get into at this stage. Will, so I think this is probably enough of my voice and presentation. So
that's fantastic. That's fantastic, and I'm sorry we can't give you a round of applause, but that's what we want to do. I wonder. No, this I think I'm worried that the session might finish at 8. It might just cut off. So I just wonder whether you got time for a few questions, and also just to ask you. And look, thank you so much. But also, one, whether we could put some students, not hundreds, but obviously a few students in touch with you if they've got more questions. But then also just okay.
Use email or WhatsApp, but email is better for me, and I always answer them. I'd be delighted to answer any student that has a question. I do it. I always do it. Yeah.
Great. Well, does anyone have any questions to ask now? I mean, there's been some really good questions in the chat thing on the side of the screen, but does anyone like to actually speak up and ask a question out loud? If not, I could ask. If Chris Leung, who teaches with us, has been asking some brilliant questions. One of which was how well, he asked when he looked at Eastgate, but how transferable do you think the design principles you've adopted to other climate types? But in a way, I think you've answered that question by showing the different projects. I mean, what's so nice about what you do is that there's so many, as you say with the Australian project, you've built in so many different kinds of technologies to almost test or prototype, and that seems to be part of the way that you work. You kind of like nature, you are a profligate prototyper, so seems like
That's right. I mean, what I've shown you really are 3 buildings in 3 climates, in 3 different cultures and 3 different economies, and they look totally different. So the architecture of green is actually related to those 3 factors: the culture, the natural environment, and the economy, plus the fact that it has to be far more adaptable because of climate change. So it has to adapt to a market which, even while you're building the building, changes.
Well, that's what's so nice about the way you finished up, that you end up talking about the economy and
That's right. Now, this one I've shown you here is absolute hell. This is about the worst climate. It's hot and damp in Hong Kong, near Hong Kong, and so you're totally different strategy. But you don't get there if you leave it to the engineer. I mean, I'm very distressed at. I've been asked to review some designs of an architect from Cape Town, who and it's for a building in Somalia, in Mogadishu. Now, I was very rude because 90% of the presentation is these damn renders. I hate renders. I hate these awful lifestyle renders that you keep dishing out to clients. They don't mean a damn thing. They all look exactly the same. You know, they're all these sort of, they don't, you know, this architect in Cape Town hasn't even thought about there's no engineering input at all in the first presentation. And that is a huge failure. I would give it naught, actually. I just fail every time. And I've now redesigned. I redesigned it and sent the redesigns to him, and they just ignored it. They just said, "Oh well, there are different ways of doing things." But I mean, I don't think there is. I think this approach has to be what we do. We have to work with engineers now, and we have to. Everything has to be science-based.
Yeah. Chris, have you got a question you'd like to ask? Oh, here's Chris. Excellent.
So Mick, I don't know if you can hear me. I've unmuted my microphone.
No, it's fine.
First of all, thanks for the amazing presentation and kind of going quite deep into the way that you've coupled understanding of engineering principles to how they're expressed as shapes, building forms, orientations on a site, and relationships to other buildings around them. I just wanted to ask you to elaborate a little bit on one of the dimensions for energy exchange between a building and its environment. I think it's really overlooked, and I think actually isn't very well understood. And just because you've given such great examples and talk about them for their cooling benefit, if you could just say a little bit more about how the fractal cooling and the fractal geometry of the outside of the building relates to, particularly when you've got a large number of clear sky nights, the kinds of cooling capacity that buildings can have. Because I think everyone's gotten so used to this idea that you've got gains from shortwave radiation from sunlight, but there's this whole other half of the day across a year where if you do have clear skies, you've actually got tremendous cooling potential back out to the sky. And I think probably one of the reasons, particularly in the UK, why we're not very familiar with the concept and we very rarely get to engineer it into a building is because we don't have particularly dark or clear skies, just as a fact of life because of the climate. But in the areas of the world that you work in, you clearly do. So if you could say a bit more about that, it would be amazing. And thanks again for the presentation.
Yeah, look, even in the UK, if you look at the swing, you do get some swing. And this guy in Cambridge who makes phase change material, he says he uses it in England for cooling. Now, the first building to use chilled ceiling panels, used it, and it was the London City Council, or London Council building, the ancient one, LCC headquarters. It was cooled with water from the Thames and pumped through ceiling panels. So there's an example of using what's available on site. Way back in, when I was at the AA, it goes back to the 60s or earlier, I think. Yeah, much earlier, I suppose. So what I do is, first of all, study the climate on the site. And you can get most of that information, that data, from the internet now, but particularly from the local aerodrome or something like that. You can get the data, but somebody will know about the particular microclimate and find out what, as much as you can, and look for ways. And that drawing, actually, I was trying to find it here. We found this guy called Mahoney in Melbourne. Here we are. This guy, he made this drawing for me, and it's a particularly difficult climate in Melbourne because of these anticyclones. But you can, if you work from that diagram, work out how to cool that building, because you can cool it passively and combine that with active interventions. So it's a combination of both, and that's, I think, what we achieved in CH2, combining active and passive in the right proportion. Because the one thing about Melbourne's climate was it's very predictable. You can almost ring up southern Australia and find out what you're going to get in the next day, because that cyclone is going to move. and it's going to come across to Melbourne. So you can almost program your building to work with work a day ahead, because quite often these passive systems take time to readjust. You know, I'll give you an example. When we were trying out Eastgate, and I'll show you here, and this is where the architect has to understand what the engineers are talking about. When we were designing, when we were tuning, sorry, I'm doing this the wrong way around. When we were tuning in Eastgate, we found that you have to, it'll take a whole year to tune the building, because you've got to go through every season. And when I started talking about, here we are, somewhere along here, there was it was perhaps in the talk. It was in the TED talk. I remember the slide with, I think I put it here actually, no, probably haven't. With the diagram of the diagonal shift. In fact, it's worth finding that. Let me just quickly get it, because it's in our documents. Here we are. Go to TED Talk. I won't bore you with the. You see, no, try on words. Let's try this. Any of these. TED Talk to. I'll probably do it here. Come on, open. Here we are. Here we are. Now you see this diagram on the right. It looks very boring stuff for architects, but it's not. It's fantastically interesting. Here's the diurnal shift. That's the night temperature. That's the day temperature. Now, the swing is about, the diurnal swing is about 10.3. Then we measure the temperature in the room, and you see stratification 1.4. That means the temperature at the floor level is cooler than the temperature of the ceiling by 1.4, as you'd expect. Hot air rises. If you, that immediately thinks about the height of the room. You can get away with a much higher temperature if there's enough stratification. In other words, tall ceilings keep you cool. I'm much worried about cool in the tropics, because to cool a building is much more expensive in energy than heating, much more, particularly with modern systems. So finding a passive way of cooling to work with the active way is well worth doing. Now this guy in Arabs gave me this thing, and he said, look, the blue line here shows that we're not cooling, we've got the timing of the changeover from day fan to night fan wrong, because it's Monday is cooler than Tuesday, which is cooler than Wednesday. And then you have to notice that meant adjusting the timing so that it was slightly different for each day. And then we decided that the fans should be controlled, or the changeover should be controlled by thermometers. And then in the office pattern, you get 5 days of the week of use. And the weekend gives you time for the building to cool down in offices. But you also get the office, the rush hour. Everybody goes to work immediately. And huge amounts of energy is used to get them there, and huge amounts is to get them back. If you start putting, like I'm doing now, housing in the office buildings, the old office buildings, you change the whole cycle of energy in the city, because you actually do away with the rush hours. And so these swings alter So in a way, you've got to look at it like doctors look at your physiology, how the body works. So it's more than just pure engineering. It's physiology. It's a process. It's a process of cycles. Now, when we were testing, we had 3 years to test Eastgate and adjust the fans. And we had to study it because we wanted to know, everybody wanted to know how it worked. And at one stage, somebody turned the fans off, and we didn't know they'd been turned off because we didn't have a proper data collection. And the building got hotter and hotter, and I got more and more worried, and I was about to leave the country and go and disappear altogether because everything looked as though it was failing. And then we found the fans had been running for 3 months. It took another 4 months for the building to cool down after we found the mistake. That was the lag time. So, there's a seasonal variation. There are all sorts of different variations, and you have to measure this and make it understandable to ordinary people. CH2 has been operating now for 12, 14 years. And it hasn't achieved its design efficiency yet because of actually poor management or uninformed management. So to run buildings that have passive and active systems, you actually need quite highly qualified people. And that's sad. That's not what I'm after. I'm after very simple solutions for management of buildings. So we haven't got there yet. It's very important that architects actually learn about this at college from their physics and their thermodynamics. We all need to learn the 2 laws of thermodynamics and understand them and be able to apply them. Sorry.
Okay. Well, on that basis, that's what we're gonna start with tomorrow. But look, Mick, thank you so much for the talk today. It's absolutely.
Yeah, when I'm in England, I'll be in London eventually.
Well, when you're here, then hopefully we can welcome you into the building and give you a big round of applause. But right. thank you again, and I'm sure a few students will be in touch. Sure. I know they will. But that was terrific, Mick. That was absolutely brilliant.
Good. Smashing. Bye now.
Yeah. Our first talk from Harare, so excellent. Speak.
Right. Shall I turn off? I'll turn off now. Right.
Okay, and I might forward some of the questions that have been typed in.
Yeah, no, that's fine. Do that, and then I'll answer them.
Fantastic. Thanks a lot. Speak soon.
Right. Great, Will. Okay. Thanks.
Bye. Bye. Thank you.